Welcome back to the deep dive. I want to start today's conversation by tapping into a feeling. It's a specific kind of feeling, one that I think we all experience, probably more often than we'd like to admit.
Okay.
You wake up in the morning, maybe you grab your phone and, and you scroll through the news for 5 minutes, or you get stuck in traffic and you just look around at all the millions of people going in millions of different directions.
Oh, yeah, I know that feeling.
Or maybe you just look up at the night sky and you realize how just vast the dark is. And you have this thought, this is a bewildering place.
It is, isn't it? Bewildering is the perfect word for it. It feels chaotic, utterly chaotic sometimes.
It really is. We find ourselves in this bewildering world, and as human beings, we have this innate, almost desperate need to make sense of it.
We can't help it.
We can't. We aren't content to just exist, eat, sleep, and repeat. We look around, we ask the big ones, what is the nature of this universe? What is our place in it? Where did it all come from? And maybe the most important one, why is it the way it is? Why isn't it just different?
Those are the fundamental questions. I mean, they're the engine of human history, really.
Mm-hmm.
That drive, that curiosity is what pushes us from myth to math. We just want to know the rules of the game we're playing.
Exactly. And today, we are taking on a heavy hitter to help us figure out those rules. We are looking at the conclusion of a massive exploration of time and space. And, I should add, some absolutely fascinating, and I have to say slightly gossipy, biographical details that come with it.
Ah, so not just the equations.
Not just the equations, we are diving into the final thoughts of A Brief History of Time.
It's a classic for a reason. And what's crucial here, for our deep dive, is that we aren't just going to be summarizing physics. We're not going to make you do calculus in your head while you're on the treadmill or whatever.
Right.
We are looking at what the source calls the world picture.
The world picture. I like that phrasing.
Yeah, it's about how we conceptualize reality. Because whether you realize it or not, you have one. You have a mental model of how the universe functions. And that model, well, it dictates how you interact with everything around you.
And the source starts with this incredible image that I just love. It's the Tower of Tortoises.
Ah, yes. The classic. A great starting point.
So for you, our listener, let's just set the scene. Picture a well-known scientist. Some say it was Bertrand Russell. Maybe it was someone else. He's giving a very serious public lecture on astronomy.
A whole 9 yards.
The whole thing. He's explaining how the Earth orbits the sun and how the sun, in turn, orbits the center of a vast collection of stars called our galaxy. He finishes, he's feeling very accomplished. And at the end, a little old lady at the back of the room stands up and says, "That's rubbish. The world is really a flat plate supported on the back of a giant tortoise."
I love that story. Just the
Exactly.
confidence of it.
It's amazing. And the scientist, he smiles, this sort of smug academic smile, thinking he's got her cornered with logic. He asks the obvious follow-up, but what is the tortoise standing on?
And she doesn't miss a beat.
Not a single beat. She shoots back, "You're very clever, young man. Very clever. But it's turtles all the way down."
An infinite tower of tortoises. And that's her world picture.
Yeah.
It's complete. It's self-contained, in a way.
Now, it sounds ridiculous to us. We laugh at it. It seems primitive, a relic of a pre-scientific age. But here is where the source gets really interesting and where the first big aha moment hit me.
Yeah.
The text makes this incredibly provocative comparison. It compares that Tower of Tortoises to modern superstring theory.
That is a bold move. I mean, you're comparing a flat Earth myth to arguably the most advanced, mathematically complex physics we have.
It is. It seems like a category error at first. Because on one hand, you have this quaint myth. On the other, you have the most advanced, mathematically precise theory of the universe we have. But the source points out a commonality that just forces you to stop and think.
They are both theories of the universe.
They are.
They both attempt to explain the foundation of everything. What is the ultimate reality made of? Is it strings? Is it tortoises? And here is the kicker, the point that really lands. Both of them lack observational evidence.
That's the thing that just blew my mind. I mean, no one has ever seen the giant tortoise at the bottom of the stack.
Nope.
But no one has ever seen a superstring either. They're too small, way too small to ever be detected by any machine we can currently conceive of.
Precisely. They're both constructs, mental models, that we use to try and explain the foundation of reality. Now, obviously, superstring theory is, well, it's far more mathematical. It has a rigorous internal structure that the tortoise theory completely lacks. You can use it to calculate things, make predictions.
Sure, it's not just a story.
Not at all, but purely from a standpoint of, have we seen it with our own eyes? Or have we detected it with an instrument? Well, they're in the same boat. We are building these elaborate models to explain what we ultimately can't see.
Although the source does point out one major practical flaw in the tortoise theory that superstrings don't have. A very, very big flaw.
Which is?
The tortoise theory predicts that if you walk far enough in one direction, you eventually fall off the edge of the world.
Which, generally speaking, hasn't been found to agree with experience. We have plenty of people circumnavigating the globe who haven't plummeted into the cosmic abyss on the back of a tortoise.
Generally. But I love the little joke the source throws in here. It says people don't fall off the edge, and I'm quoting, unless that turns out to be the explanation for the people who are supposed to have disappeared in the Bermuda Triangle.
Yeah, a little physicist humor there. But that comparison, it really sets the stage for the journey we're taking today, doesn't it?
Yeah.
We are tracing how humanity moved from spirits to uncertainty.
A huge leap.
A monumental leap. Because before we had math, and even before we had the tortoises, we had spirits.
Let's unpack that. Because this really is the evolution of our world picture. We didn't start with equations or even with simple physical models.
Right. If you go back to the earliest theoretical attempts to explain the universe, everything was personal. It was all about agency. Events weren't driven by abstract forces like gravity or electromagnetism. They were controlled by spirits with very, very human emotions.
The river spirit, the mountain spirit, the volcano spirit.
The sun god, the moon goddess. And these spirits were capricious. That's the key word. They acted in a human-like, unpredictable manner. If a flood happened, it wasn't because of rainfall patterns and drainage basins.
No, it was because the river spirit was angry.
Exactly. Or bored.
Yeah.
Or vengeful. Who knows?
Yeah.
So the physics of the day, if you can call it that, was basically negotiation.
It was diplomacy with the cosmos.
That's a great way to put it. You made sacrifices. You tried to placate them. You performed rituals. You gave gifts. It was a transactional relationship.
Please, sun god, if I do this dance, will you rotate the season correctly so my crops grow?
Yes. You behave, and hopefully nature behaves in return. And that's a terrifying way to live, because you never know if the deal will hold. The gods might just change their minds.
But then a shift happened. A really profound shift in human consciousness. People started noticing patterns, regularities.
Yes, they noticed the sun rose in the east.
Every single time.
Whether you sacrificed a goat or not, whether you were nice to the river spirit that day or not, the sun rose in the east and set in the west. The planets, these wandering stars, followed precise, predictable paths across the sky. The tides came in and out on a schedule.
So the conclusion wasn't necessarily that there were no gods,
Not at first.
but that the gods, if they existed, were following rules. They were playing by a script.
Yes. They obeyed strict laws. Perhaps they were still gods, but they were bound by a cosmic constitution. They couldn't just do whatever they wanted on a whim. And this realization, this discovery of regularity, paved the way for what we now call scientific determinism.
Which brings us to a giant of the 19th century, Laplace. This is where we really start getting into the machinery of the universe, the idea of it as a machine.
The Marquis de Laplace. He really formulated the ultimate dream of classical science. He was a brilliant mathematician, and he took Newton's laws and ran with them.
So what was his hypothesis exactly?
He postulated that if you knew the configuration of the universe at one single moment, and by that, he meant if you knew the exact position and the exact speed of every single particle in existence.
Every atom, every quark.
Everything. If you had that one perfect snapshot, and if you knew all the laws of physics, you could, in theory, calculate the entire future of the universe and perfectly reconstruct its entire past.
The clockwork universe. You just need to know how it's set at one moment and you can see the whole clock.
Completely determined. If this were true, there is no ambiguity. There's no chance. If I know exactly where every atom in your brain is right now and how they are all moving, I can predict exactly what you're going to say next. I can predict what you'll have for lunch in 10 years.
That's a little terrifying. I mean, it kind of removes free will from the equation, doesn't it?
Oh, completely.
It suggests we're just cogs in a machine that was wound up at the beginning of time and is just playing out.
It does. It suggests everything is prescripted by the laws of physics.
Yeah.
It was a very confident time for science, a very arrogant time, you could say. We thought we had it all figured out, or at least on the verge of it.
But there's a theological angle here that the source points out, which I found fascinating. Laplace didn't rule out God entirely in this model, did he?
No, but he demoted God. He limited him significantly.
Yeah.
In Laplace's view, God had two jobs and only two. One, choose the laws of physics.
Okay.
Two, choose the initial configuration of the universe.
Right.
Wind the clock and set the hands at the very beginning. But once the universe started, God steps back. He becomes a non-interventionist watcher. He doesn't interfere.
God is confined to the beginning. The moment of creation is the only place he can act.
Exactly. God was confined to the areas that 19th century science didn't understand yet, which is usually how it goes. We call it the God of the gaps. As science advances and explains more, the gaps for God to hide in get smaller and smaller.
And Laplace famously told Napoleon, "I have no need of that hypothesis," when asked where God fit into his model of the solar system.
Right. He meant he didn't need God to nudge the planets to keep them in their orbits. The laws took care of that.
But then the 20th century comes along and just crashes the party. Laplace's beautiful, predictable, deterministic dream, it gets shattered.
Completely shattered. Utterly and completely. And the sledgehammer that broke the clock was the uncertainty principle.
Heisenberg.
Werner Heisenberg. Yeah. In the 1920s, as we started to probe the world of the very, very small, the world of atoms and electrons, we discovered something fundamental and deeply weird. You simply cannot measure both the position and the velocity of a particle with complete accuracy at the same time.
And I want to be really clear on this point because it's so easy to misunderstand. This isn't just because our rulers aren't precise enough, right? It's not a technological limitation.
Absolutely not. It's not like, oh, if we just had a better microscope, we'd be able to know.
Yeah.
It is a fundamental property of nature itself. The universe has a built-in fuzziness.
So how does that work? Why can't we know both?
Well, think of it this way. To measure a particle, you have to interact with it. You have to look at it, right? And to look at something, you have to shine light on it. But light isn't just a gentle wave. At the quantum level, it acts like a stream of tiny bullets, particles called photons.
Okay.
So when the light hits the electron so you can see where it is, that photon actually dumps the electron. It transfers energy to it. So by the very act of measuring precisely where it is, you've changed how fast it's going. You've disturbed it.
You can't look at the universe without disturbing it. The observer is part of the system.
Exactly. And it works the other way, too. If you use a very low-energy photon to not disturb its speed, that photon has a long wavelength, which means you get a very fuzzy idea of its position. There's an inescapable trade-off. The more you know about one, the less you know about the other.
So if you can't measure the current state of the universe accurately, which is the absolute foundation of Laplace's theory,
Then the whole thing collapses.
you certainly can't predict the future accurately.
Precisely. If you don't know exactly where the particles are and exactly where they're going now, you can't possibly calculate where they will be later. The clockwork is broken, or at least we can never read the clock face with enough precision. We had to redefine the entire task of science.
How so? If we can't predict exactly what will happen, what are we even doing? What's the point of physics?
Well, we moved to quantum mechanics, a whole new framework. We stopped trying to predict specific events like this electron will be right here at 2 p.m. on Tuesday, and we started predicting probabilities. We predict the evolution of a mathematical thing called a wave function.
A wave of probability.
Basically, yes. We can predict with incredible accuracy that if you do an experiment 1,000,000 times, 30% of the time the electron will be here, and 70% of the time it will be over there. But for any single electron, we have no idea which it will be. Randomness is baked into the very fabric of reality.
And this is where it gets really trippy for me. The source suggests that maybe our confusion, maybe this whole randomness thing, comes from trying to force reality into the wrong box.
Yes. This is a very provocative thought from the book. It asks, what if there are no definite particle positions and velocities to begin with? What if that's just a concept in our heads, a hangover from our experience with billiard balls and planets? What if, at the fundamental level, there are only waves?
Wait, unpack that for me, because I feel like I'm made of particles. This table feels like it's made of particles.
Right. We think of a particle as a tiny little ball. It has a definitive place, a definitive speed. But the source suggests that this unpredictable random element only comes into play when we try to interpret these fundamental waves as if they were particle positions.
So the randomness is our fault. It's an artifact of our measurement.
In a way, yes. It's a mismatch between what reality is, which might just be these evolving waves of potential, and our preconceived idea that reality should be made of tiny, definite particles. We are trying to fit a square wave into a round particle hole, and the result of that mismatch is what we perceive as uncertainty and randomness.
We are forcing the universe to answer a question it wasn't designed to answer. Where is the particle? And the universe replies, it's not a particle, it's a wave, so that's a bad question.
That's a fantastic way of putting it. But even with this new quantum picture, even if it's all waves, we still have laws. We have the Schrödinger equation, which predicts how the wave evolves perfectly deterministically. The question remains, though, who or what chose those laws? And who chose the initial state? Because even if it's a wave, someone had to start the wave rippling in the pond.
Which brings us to the great sculptor of the universe, gravity. We need to talk about gravity because it changes the game for what a beginning even means.
Gravity is the odd one out. It's the weakest of the four fundamental forces by a long shot. I mean, think about it. A tiny fridge magnet can pick up a paper clip against the gravitational pull of the entire planet Earth.
That's a great point. The whole planet is pulling down, but this little 1-inch magnet pulls up and the magnet wins.
That's how incredibly weak gravity is. But it wins in the long run.
It wins on the large scale.
Right. It shapes the structure of the cosmos, galaxies, stars, planets, because it acts over infinite distances. And crucially, it is always attractive. It always pulls. And the source highlights a big problem that gravity poses for the old idea of a static, unchanging universe.
Because gravity always attracts. It never pushes away.
Always. It's always pulling things together. So a universe ruled by gravity simply cannot be static. If you just leave a bunch of stars out there in space, gravity will inevitably start pulling them toward each other. The universe must be either expanding or contracting. It has to be dynamic by its very definition.
And this leads us directly to the Big Bang.
Right. Observations in the 1920s showed that distant galaxies are moving away from us. The universe is expanding. So if it's getting bigger now, that means in the past, everything must have been closer together.
You just rewind the tape.
You rewind the tape far enough, you get to a point where everything in the entire observable universe was crushed into a single point of infinite density, a singularity. The Big Bang, the beginning of time itself.
And potentially the Big Crunch, the other end of the tape.
That's the theoretical opposite, yes. If there's enough matter in the universe, its collective gravity might be strong enough to eventually stop the expansion and pull everything back together into another point of infinite density, the Big Crunch, the end of time.
And the source mentions that black holes are sort of localized versions of this, a personal Big Crunch.
Exactly. For anyone or anything unlucky enough to fall into one, it's a localized singularity, an end of time just for you.
Now talk to me about singularities, because this seems to be the place where physics throws up its hands and says, we don't know.
That's pretty much it. A singularity like the one at the Big Bang, or the center of a black hole, is a point where the curvature of space-time becomes infinite, the density is infinite, the temperature is infinite, and crucially, it's a point where all the known laws of science break down.
They just stop working, like a calculator trying to divide by zero.
That is the perfect analogy. The math just returns error. You can't calculate what happens at or through a singularity. It's an edge, a boundary. And this is absolutely vital for the theological argument.
How so?
Well, if the laws of science break down at the Big Bang, then science cannot predict how the universe began. It can describe what happened a fraction of a second after the bang, but the moment of creation itself is outside its jurisdiction.
So that leaves the door wide open for a creator.
Exactly. It leaves a gap, a massive one. If the laws of physics don't apply at the moment of creation, then a creator would have complete and total freedom to choose how the universe began, what it was made of, everything. Science can't touch that moment. It stops at 1 second after. But the bang itself, that's off limits to physics.
Okay, but this is where the source material drops the hammer. This is the big pivot, the no boundary proposal. This changes everything regarding that gap.
It really does. This is the bleeding edge. This is the attempt to combine quantum mechanics with general relativity gravity with the quantum world.
Yeah.
It's the holy grail of modern physics. And when you try to do that, you get a new mind-bending possibility for the shape of the universe.
Visualize this for us, because no boundary sounds very abstract.
Okay, so imagine the surface of the Earth. It's finite,
Yep.
right? It has a specific size. You can measure its surface area in square miles.
Right. It's big, but it's not infinite.
Exactly. But it has no boundary. You can never fall off the edge of the Earth. You can get in a plane and fly in a straight line, and you'll never hit a wall. Eventually, you'll just come back to where you started.
Right. No edge, no boundary, but a finite area. Got it.
Now, think about the North Pole. Is the North Pole a beginning of the Earth? Is it an edge?
No, it's just a point on the map. It's a place.
Yeah.
It's not a cliff you fall off of.
Exactly. The North Pole is just a normal point on the surface of the Earth where the lines of longitude all happen to meet. There's nothing south of the South Pole, and there's nothing north of the North Pole. But that doesn't mean there's a boundary there. It's just a feature of the geometry of a sphere.
Okay, I'm with you. So it's a special point, but not a broken point.
Perfect. Now, bump that whole idea up to 4 dimensions, 3 of space and 1 of time, all woven together. The no boundary proposal suggests that space-time is like the surface of that Earth. It's finite, but it has no boundaries and no singularities.
So no sharp point where everything breaks down, no point of infinite density where the math fails.
Exactly. No beginning and no end. In this model, the universe just is, and asking what happened before the Big Bang becomes a meaningless question. It's like asking what is north of the North Pole.
It's not a mystery, it's just a nonsensical question based on a flawed premise.
Precisely. The word before assumes a boundary, a starting line for time that might not exist.
If that's true, and I know it's a huge if, what does that do to the role of a creator? The one who was supposed to be in that gap at the beginning.
It's the ultimate question, isn't it? If the universe is completely self-contained with no singularities and no boundaries, then it doesn't have a moment of creation in the traditional sense.
Right.
It doesn't have that moment where a finger came down from outside the system and pressed start.
The source quotes Einstein asking, how much choice did God have in constructing the universe?
And if this proposal is right, the answer might be not much, or maybe even none at all.
Unpack that. How could there be no choice?
Well, if the no boundary proposal is correct, God had no freedom to choose the initial conditions because there was no initial moment to choose. The universe is a self-contained loop. It wasn't set up at a particular time because time itself is part of the loop.
So God's only remaining choice was the laws themselves, deciding how gravity works, how quantum mechanics works.
Even that might be limited. And this is where it gets even stranger. The source suggests there might be only one, or very few, self-consistent sets of laws, like a specific version of string theory called heterotic string theory, that allows for a universe complicated enough to produce structures like galaxies, stars, and ultimately creatures like us who can ask these questions.
So you're saying God couldn't just make any universe. He couldn't have made gravity a repulsive force, for example, because the math just wouldn't work out to create a stable reality.
It's possible. If there's only one mathematical possibility that is self-consistent and leads to complexity, then God didn't really have a choice in the laws either, which leads to the heaviest question in the entire book. If the universe is self-contained, has no beginning, no end, and is defined by the only possible set of laws, what is the role of a creator?
It doesn't disprove God, but it certainly changes the job description.
It removes the job of cosmic starter and divine lawmaker. It implies that the universe couldn't be any other way. It is the way it is because it's the only way it could be.
But this leads to this section that, I have to admit, gave me chills. Because even if we have the perfect math, the one perfect, elegant, unified theory, something profound is still missing.
A fire.
Yes. The quote is, what is it that breathes fire into the equations and makes a universe for them to describe? That question just, it stops you in your tracks.
It really does. It strikes at the fundamental distinction between the what and the why. You can have a perfect mathematical model, a complete theory of everything that describes every force and every particle. But that model is just a set of rules. It's just ink on a page or code in a computer. It doesn't explain existence itself.
Why does the universe go to the bother of existing?
That's the phrase from the book, the bother of existing. It's such a human way to put it. Is the mathematical theory so powerful, so compelling, that it somehow brings about its own existence? Can an equation create a rock? Or a star?
Or a human being?
Or does it need a creator to breathe that fire into it, to instantiate the math, to make it real? And if it does need a creator, then we're back to the old question, who created the creator? It doesn't stop. It turtles all the way down again, just on a much more abstract level.
And the source material gets a little spicy here regarding who is supposed to be answering these questions. It takes a serious jab at modern philosophy.
Oh, it's a roast. A full-on academic roast. It does not hold back.
Walk us through the decline of philosophy as described in the text, because, traditionally you'd think philosophy and science go hand in hand.
Well, historically, they were the same thing. In the 18th century, philosophers were the heavyweights. They studied all of human knowledge. Science wasn't even called science yet. It was just natural philosophy. People like Kant were asking the big questions. Did the universe have a beginning? They were engaging directly with the physics of their time. They were in the room where it happened.
But then physics got hard.
It got very technical and very mathematical very quickly. In the 19th and 20th centuries, with relativity and quantum mechanics, most philosophers couldn't keep up. The math became a huge barrier to entry. To have a serious discussion about the nature of time, you had to understand general relativity and complex calculus, and that is not something you can just pick up over a weekend.
So they retreated. They gave up on those questions.
They narrow their scope dramatically. The source quotes Wittgenstein, who is arguably the most famous and influential philosopher of the 20th century, saying that the sole remaining task of philosophy is the analysis of language.
Just words.
Just analyzing how we use words. And the source's reaction to that.
What does it say?
It says, what a come down from the great tradition of philosophy from Aristotle to Kant.
Ouch. That is a scorching hot take.
It is, but it highlights a real problem, a real gap that has opened up. The scientists are so busy describing what the universe is that they often don't have time to ask why. They're deep in the weeds of the equations. And the philosophers, whose entire job it is to ask why, have largely been shut out of the conversation because they can't understand the modern language of physics, which is mathematics.
We're kind of drifting in a sea of how without a captain of why.
That's a really good way to put it. We've optimized the mechanism, but we've lost the manual for what it's for. We know how the car engine works down to the last bolt, but we've forgotten where we're supposed to be driving.
Now, speaking of the people who built the engine, I want to transition to the giants. The source material includes these short, wonderful biographies of Einstein, Galileo, and Newton, and I have to say it really humanizes them. And by humanize, I mean it shows they could be petty, political, and frankly, very messy people.
Oh, absolutely. We tend to view these figures as these abstract brains in jars, pure intellect, disconnected from the mundane world. We put them on pedestals. But the source paints them as vivid, passionate, and deeply flawed people.
Let's start with Einstein. The source says his life was divided between politics and equations.
Which is such an interesting duality. We all know the equations, ihm sei Auer, but the politics defined his life just as much, if not more.
He was a pacifist, right?
A staunch one. During World War I, while he was in Berlin, he was just sickened by the senseless waste of life. He was one of only a handful of academics to protest it. He publicly advocated civil disobedience and told people to refuse conscription.
That could not have made him popular in wartime Germany.
Not at all. He was very unpopular with his colleagues. And then later, of course, he became a target for a different reason, his Zionism and his Jewish heritage.
The source mentions he was Jewish by descent, but he had rejected the biblical God.
Correct. He wasn't religious in a traditional sense. But as he saw anti-Semitism rising in Germany in the 20s and 30s, he identified more and more strongly with the Jewish community out of a sense of solidarity. And because of his fame and his background, he became a huge target for the nationalists.
To the point where an organization was set up specifically to debunk him.
Yes, 100 authors against Einstein. Can you imagine that? An entire book, a collection of essays written just to say you're wrong.
And this gives us one of the greatest comebacks in scientific history. When Einstein heard about the book, he just shrugged and said, if I were wrong, then one would have been enough.
Thumb drop. Absolute mic drop. But the real tragedy of Einstein's life, as the source points out, is the bomb. He was a committed pacifist, but he was terrified that the Nazis would develop the nuclear bomb first.
So he signed the famous letter to President Roosevelt urging the U.S. to build it.
A pacifist initiating the atomic age. It's a terrible, terrible irony. And after the war, he spent the rest of his life campaigning for international control of nuclear weapons. He regretted it deeply and tried desperately to put the genie back in the bottle.
There's one last detail about Einstein that I just loved. In 1952, he was offered a job, a pretty big one.
The presidency of Israel.
Imagine that, President Einstein. It sounds like something out of a science fiction novel.
He turned it down, of course. And his reasoning is just beautiful. He said, politics is for the present, but an equation is something for eternity.
Wow, that's perspective.
Deep perspective. He knew where his true value lay, and it wasn't in an office.
Let's move back in time from there to Galileo, the rebel.
Galileo is really the father of modern science, not just for his discoveries, but for his attitude. He believed in observation over authority. But he was also a bit of a populist, which is what really got him in trouble.
He wrote in Italian, not Latin.
Which was a huge deal. We take that for granted now. But back then, all serious academic books were written in Latin. That was the gatekeeping mechanism. Only the elites, the priests, and the university scholars could read them. Galileo wrote in the common language of the people. He bypassed the professors and went straight to the public.
It was the 17th century equivalent of posting your groundbreaking research on Twitter instead of in a locked paywall journal.
That's a perfect analogy. And the academic establishment hated him for it. The Aristotelian professors, as the source calls them, united against him. They couldn't beat his arguments, so they used the church to do their dirty work. They framed his science as heresy to get him silenced.
And this is the famous conflict. The Earth goes around the sun.
The Copernican theory. The church, under pressure from the academics, declared it false and erroneous in 1616. Galileo was officially warned to shut up about it, and he did, for a while.
Until a friend of his became pope.
A classic political miscalculation. He thought having a friend in high places meant he was safe. He got permission to write a book, The Dialogue Concerning the Two Chief World Systems, on the strict condition that he remained neutral and presented both sides fairly.
He did not remain neutral, did he?
Not even close. He wrote it as a dialogue between three characters. The one arguing for Copernicus's sun-centered model is brilliant and witty. The one defending the old Earth-centered view is named Simplicio, which basically means simpleton. And to add insult to injury, he put the Pope's own favorite arguments into Simplicio's mouth.
Oh, wow. So he didn't just poke the bear, he dressed it up in a clown suit and embarrassed it in public.
It was a deep betrayal. The Pope was furious. It wasn't about theology anymore. It was personal.
So the Inquisition, house arrest for the rest of his life.
For life. He was an old man, going blind, locked in his house near Florence. But, and this is the triumph of the story, he didn't stop working. He wrote his second and arguably more important major book, Two New Sciences, while under arrest.
And he smuggled it out.
Smuggled the manuscript out, page by page, to a publisher in Holland, beyond the reach of the Inquisition. That book, written by a prisoner, became the genesis of modern physics. You can lock up the man, but you can't lock up the ideas.
Incredible. Now, from the rebel to, well, to the not a pleasant man, Isaac Newton.
Yeah. The source material does not pull any punches here. It literally opens his short biography with the sentence, Isaac Newton was not a pleasant man.
We think of the apple falling from the tree, discovery of gravity, this serene moment of genius. We don't think of the vengeance.
He was, by all accounts, an incredibly vindictive and solitary man. The source highlights two major disputes. First, the one with John Flamsteed, who was the first astronomer royal.
What happened there?
Newton was writing his masterpiece, the Principia. He needed astronomical data to check his theories of gravity. Flamsteed had the best data in the world, but he was a careful scientist. He wasn't ready to publish it yet. He wanted to check it, make sure it was perfect.
And Newton wasn't a patient man.
Not at all. He wouldn't take no for an answer. So what did he do? He used his political influence to have himself appointed to the governing body of the Royal Observatory, and then he forced the publication of Flamsteed's data against his will. He essentially seized Flamsteed's life's work.
He stole the data.
He did. Flamsteed was so incensed that he took Newton to court and actually won a court order to stop the distribution of the stolen book. He managed to buy up most of the copies and personally burned them.
Good for him.
But Newton got the last word. He was so angry that in later editions of the Principia, he systematically went through and deleted every single reference to Flamsteed's contributions. He tried to erase him from the history he helped create.
That is just, it's so petty. It's high school level petty, but with the laws of the universe at stake.
And it gets worse. The dispute with the German philosopher and mathematician Gottfried Leibniz.
This is the big one. Who discovered calculus?
Right. And the historical consensus now is that they both discovered it independently. Newton got there first, but he was secretive and didn't publish. Leibniz discovered it a bit later, but published it right away. A massive, bitter row broke out across Europe over who had priority.
And Newton was the president of the Royal Society at this time, which was like the high court of science.
The judge, jury, and executioner. Leibniz made the terrible mistake of appealing to the Royal Society to resolve the dispute impartially. Newton appointed an impartial committee to investigate.
Let me guess. The committee was not impartial.
It was made up entirely of Newton's friends and supporters. But that wasn't even the worst part. Newton secretly wrote the committee's final report himself, which of course accused Leibniz of plagiarism. And then, and this is the truly diabolical part, he wrote an anonymous review of his own report in the Royal Society's journal, praising it for its thoroughness and fairness.
Wow, that is House of Cards level political maneuvering. It's unbelievable.
And after Leibniz died, impoverished and with his reputation tarnished, Newton reportedly boasted that he took great satisfaction in breaking Leibniz's heart.
Yikes. So, not a nice guy. But the source mentions he had a later career where he actually put this talent for deviousness and vitriol to use.
He did. He became warden of the Royal Mint.
A cushy government retirement job.
It was supposed to be. But Newton was not a man to do things by halves. He took it incredibly seriously. He launched a major campaign against the counterfeiters who were debasing England's currency. He didn't just sit in an office, he went undercover. He disguised himself and hung out in taverns and prisons to interview witnesses. He used his incredible intellect and his utter ruthlessness to track them down, prosecute them, and send them to the gallows.
So the man who discovered the universal law of gravitation also spent his golden years personally seeing to it that people were hanged for making fake coins.
A very complex figure, a towering genius, but a dangerous man to cross.
It really changes how you see the equations, doesn't it? Knowing the people behind them were so human, so flawed.
It does. It reminds us that science is a human endeavor. It's driven by pure curiosity, yes, but also by ego, by ambition, by politics, and by passion. It's messy. The purity of the math often comes from the impurity and the chaos of the people who discover it.
Which brings us, I think, to the ultimate goal of all this messiness, the democratization of science.
This is the hopeful note the source ends on, the whole point of this search for a final, unified theory.
Right now, these theories, like the no-boundary proposal or superstring theory, they're locked away in incredibly complex mathematics. Only a handful of specialists in the world can truly understand them.
It's just like how, before the Reformation, only the priests could read the Bible in Latin. The common people had to take their word for what it said. We're currently in a kind of priestly phase of theoretical physics. You need a PhD and years of study just to enter the temple.
But the hope is that if we find a complete final theory, it should be understandable in broad principle by everyone.
Everyone, not just scientists. Philosophers, artists, and just ordinary people like you and me. The goal isn't to keep the knowledge hidden away in an ivory tower. It's to share it, to make it part of our common culture.
Just like Galileo writing in Italian.
Exactly like that, to bring it to the people.
And if we can all understand it, we can all get back to the big business.
The business of asking why. We can all participate in that discussion.
Why do we exist? Why does the universe exist? These become questions for everyone, not just for a select few.
And if we can answer that question, the source says, it would be the ultimate triumph of human reason.
For then we would know the mind of God.
That's the closing line of the main text. And it's such a powerful, ambiguous one. It suggests that understanding the mechanism of the universe, the what and the how, is the closest we can possibly get to understanding the intent behind it, the why. It's a bridge between the physical and the metaphysical.
So for you, our listener today, what's the final takeaway? We've covered a huge amount of ground here.
I think the takeaway is to not be intimidated by the bewildering world. We've gone from tortoises to superstrings. We've gone from capricious spirits to the no-boundary proposal. The journey is messy look at Newton, but it's a journey of progress. We're inching closer and closer to the answers.
And don't ever stop asking why.
Never. That's the most human thing we do. The equations describe the stage, but you are the one watching the play. You have to ask what the plot is. You have to ask what the director intended.
And maybe reflect on that final question for yourself. Does a complete theory of everything eliminate the need for a creator? Or is the very existence of such an elegant, powerful theory the handwriting of the creator?
That's the question to chew on. That's the one that keeps you up at night.
Thank you for diving deep with us today. This was a big one.
Always a pleasure, a real mind bender.
And to our listener, keep looking up. We'll see you on the next Deep Dive.